Okay, yeah, I think we can finally start to recording so the remote students can watch online now. So before we start today's lecture, I first want to talk about this one, the presentation schedule. We just made an announcement about the time schedule of your presentation. So basically, we divided you into like 3 groups. One group is in-person session, so which means you will come here to present. I will be here to in charge of that part. There are around 16 students to choose the in-person presentation. Another 2 groups online session, because we have so many people to choose the online session, so we have to divide you into 2 groups. For the online session, one group is a big group which has around 40 students, so it will start from 1 o'clock, same as the lecture time, and finish around 3 o'clock. Another one will be also hosted by me, because I have to do the in-person session first, and after that I will host the online session. The second online session, sorry. So this one will start from 2 and 10 and end at around 3 o'clock. So there will be 3 sessions. So make sure you check your session is right, because you fill the form before to choose which online session or in-person session you want to go. Make sure you find out whether your user ID, I didn't put the name in, so I only put the student ID. Make sure you check your ID. If you are in, that's fine. And if you say there might be some problems of your time slots, so please let us know. We can try to swap you with someone else if you find it's not suitable for you. And if you find you are not in the list, please let us know as soon as possible, because next week will be the presentation week. We don't want to make any problem. So if you find yourself is not on the list, because there are still around 10 students didn't give us any response, so we don't know you belong to the in-person or the online group. But if you are not here, sorry, please let us know, and we will try to insert you into the groups. Okay. So that's about the presentation. And again, each presentation will be 3 minutes. So you have 3 minutes to talk about your idea, the project idea. So the first presentation is about pitch idea. So basically, we want you to show your project ideas. So why you think your idea is interesting, why the application is novel and significant, and basically that's the most important part. Of course, you also need to submit your slides before, after the presentation. That's fine. We don't have a fixed deadline for this one, but you have to submit your slides at least after your presentation to the MyUnion. I think I built a link for you, so you can just submit your slides. Okay, and of course you need to have a clear planning for the next few weeks, like what's the data source you might to use for this project, right? You don't need to give us the link of the data or how many data you have. You just say, well, I need this data, and here is some sources that I can use to find all those data, right? And what kind of method you may use to solve that problem. Like you say, well, this is a typical classification problem, which I will introduce later, or this is just a regression problem. Then what kind of method? For example, if it's a classification problem, you may want to use classical SVM or KNN, right? So if it's a regression problem, what kind of things do you want to use? So show us some plan, right? Just in 3 minutes, it's a very short presentation. Okay, so that's it. That's the story about the presentation. So any questions about this one? Yeah.
How many slides does the slide have to have?
Well, we don't have any templates or restriction about like how many slides do you need to have. It's basically 3 minutes. I noticed some students just use 1 slide. So just one slide and nothing in there, just a title. That's my project, and talking 3 minutes. That's okay, but his presentation is still very good. But some students use like 5 slides, 3 minutes. Well, you cannot have 30 slides with 3 minutes presentation, right? So it depends on you, right? Okay. So any other questions? Great. So now let's start our today's, let me check. Yeah, so this is a recording, so that's good. Okay, so now let's start our today's lecture. So basically today, I want to introduce some basic technologies or basic concepts in the machine learning, right? Because your project will use some basic machine learning tools. I don't want you to, spend a lot of time on the very recent or advanced machine learning algorithms, but I do want you to have some background knowledge about what's classification it is, what's segmentation, or what's the meaning of the regression, and in what situation, in what kind of problem you need to choose what kind of algorithm. So let's have some basic stuff to introduce today. Well, I guess most of you have some knowledge about this one. Otherwise, you cannot choose this applied machine learning course. So, firstly, what is machine learning? This is a very interesting question. So basically, when we want to learn something from the data, so we can use the machine learning to learn the representation of from the training data, and we want to use the information, the knowledge we learned from the training data to help us to make some prediction or recommendation, right? That's why we need machine learning. So basically, the machine learning is an algorithm that can improve their performance using training data. So typically, the algorithm has a number of parameters whose values are learned from the data. Right? Sometimes the numbers of parameters are quite large. For example, nowadays, deep learning is very famous. I guess some of you choose the master of machine learning because of the deep learning. Without deep learning technology, actually, current AI cannot be that hot, because the deep learning makes the computer vision, makes the NLP works very well today. So that's why today the machine learning AI is super hot. There are so many companies working on the machine learning applications and the problems. And actually for the deep learning technologies, they need large numbers of parameters, sometimes millions of parameters, and sometimes for example, for the transformer, you must know the BERT, right? The famous NLP model, it has billions of parameters. And if you want to train that model, you normally need thousands of GPU. In Google actually developed their own GPU, which is called the TPU, Tensor Processing Unit, right? So it's very expensive. Normally, you must have heard the news, the OpenAI trained the BERT model cost them like how many more $1 million or something. So it's very expensive to train a machine learning models actually, because there are so many parameters in one model, and to train the model you need a lot of high-end GPUs, right? So but of course some traditional algorithms like SVM or like some method that we introduced today, like the k-nearest neighbor, the parameters are very small. For example, for the KNN, which I will introduce later, there's only one parameter, which is k. So there's just one parameter. It's so simple, but it still can solve some problems, right? So that means, basically, typical algorithm has a number of parameters, and those parameters are learned from the data. Why do we need training data? Because we want to learn the parameters from those training data, and we reuse the parameters in some testing data to give us a prediction or recommendation, right? So the machine learning can be applied in situations where it is challenging and actually impossible to define rules by hand, right? So when we see if the problem can be defined by rules, right? For example, if we know if you make the red light, you need to stop. You have the green light, you can go, right? So you can write a very simple algorithm. So it's a kind of rule based, right? This is the rule. So bigger than, so if it's 1, pass. If it's 0, stop, right? So you can write a rule. You don't need any machine learning algorithm to learn this kind of rule, because it's a simple rule, and in your algorithm you can write it by like 2 or 3 lines of code. But for the machine, for some problems, we don't have a clear rule. We cannot define a rule by ourselves. We cannot have a hand-defined rule to make it work, right? For example, like face detection, speech recognition, stock prediction. Because yes, for example, the stock prediction, I know many of you will do your project on the stock prediction. So it's a very complex thing, right? There are so many different factors will affect the stock price. So you cannot just simply write a rule. Well, of course, I think before the machine learning, or like 30 or 40 years ago, there are some so-called AI system. It's actually rule-based, right? So you can write, so they hire a lot of people to write the rules, and if some conditions meet the rules, then that means you can make some prediction. That's a rule-based system, right? But of course, for some complex problems like face detection, speech recognition, this kind of things, you cannot just simply write a rule to recognize someone's face, right? So in this case, we need machine learning to help us to make the decision. So we need to learn from the training data to get the parameters and use those parameters, use those functions to help us to solve the real problem. So here are some examples, like here is a typical machine learning. Actually, it's a typical computer vision problem. So well, machine learning is, so basically, let's talk about this. AI. AI is very big. AI is a very big topic, very big area. A lot of topics belong to the AI. And in AI, machine learning is part of AI, right? So machine learning is just part of AI. Machine learning is not equal to AI. So machine learning is just a part of AI. And in the machine learning, we also have different application level topics like computer vision. So in computer vision, we care about how can we recognize object from the images, or how to segment object from images, or even like this, OCR, how to recognize the letters, handwritten digits from the image, right? So it's basically about the image. And we also have the NLP, natural language processing. So we can use NLP tools to recognize the human speech and to do the translation, those kind of things. So it's also part of the machine learning. So because actually both of them use machine learning techniques like classification, regression, and clustering, those kind of things. So this is the first example I will give you about the handwritten digit recognition. So here, assume we have, well, this is the problem. We have from 0 to 9, this is the handwritten digits, and the images are 28 by 28 pixels, and we can represent the image as a vector, which is x belong to R, 784. Why 784? Because 28 by 28, right? So when we say we want to encode something into a vector, there are many ways, right? So deep learning, the CNN is just a kind of way to encode the image into a compact vector representation. And some other famous computer vision encoders like image encoders like SIFT features. It can also encode the image into some compact features, but still pixel is also kind of representation. So actually we can put the 28 by 28 images into a single vector, right? So which is this x. So we can, so that means we can represent the images as a vector of x. Then we want to, so for the machine learning, we want to learn a classifier fx such that give me the x is the image, right? So I want to predict whether it belongs to any of these 10 classes, right? For example, this one, If my algorithm, my machine learning algorithm is great, it's successful, then I can recognize it, I can classify it into this class 8, right? So the whole machine learning idea is that whether we can learn this function, whether we can learn this f from the training data. For example, give me hundreds of these digits. I know this is 9, this is 8, this is 7, and this is 3, right? Give me many labeled examples. Whether I can learn a function f, then next time give me a new image. For example, give me a new image of this one. It's slightly different. Then I input this image into my learned function f, and what's the output? Right, the output will be of course, for example, if the function learned is very good, then I will get this class label, which is 8. Right? That's the basic idea of the machine learning. That's just one example. Yeah, so here, how to proceed. So this is actually a typical supervised classification problem. So start with the training data. For example, in this data set, we have 6,000 examples of each digit, right? So it's a big one, actually. So with different, in different styles, for example, 0, as you can see, there are different styles of 0 and different 5 or 4. So actually, if we use the right algorithm, it can achieve very high accuracy here. One algorithm, so it's not actually the current algorithm, it's just a very old algorithm, old-fashioned algorithm. It can achieve actually testing error with just 0.4%. That means it's 99.6% successful rate, which is very high, right? So this is actually one of the first commercial and widely used machine learning system, because it's an easy one, right? So another harder example, which is face detection, and sometimes we also do the face recognition, right? So the problem of face detection is to detect the face from the image and give a label, right? So label is, here we are talking about face detection, not face recognition, right? So it's the two problems. Face detection means we want to detect, we want to give a bounding box of the face in the image. And face recognition means we want to recognize who of the person is, right? So like this is A, this is B, right? So again, this is a supervised classification problem, and need to classify image window into 3 classes, like non-face, well, maybe it's just a background, and sometimes we need to know whether it is front face or just a profile face, right? Because sometimes if it's a profile face, we will not input into the face recognition system because it's very hard to recognize someone's face if it's just a profile face. So we need a front face. So a traditional algorithm of this one is we have sliding window. So basically we have different size of the bounding boxes, and we slide it from the top left until to the like lower right. So one pixel by pixel, or we can define some slide size and one by one, and give me a window like this, and then I put into a classifier, which in that classifier has 3 class labels, and I want to classify into one of 3. Right? So this is also a typical supervised classification problem. It's face detection. So so in this problem, this here is a very it's not the latest one, but it's a very famous data set. It's training data for front faces, which has actually 5,000 faces, all near frontal, and it has different age, race, gender, and different lighting conditions. And we also have large numbers of non-faces, not just background images, as a negative example. So but when you want to train a classifier, you need to have the positive example and you need to have the negative example. Or if it's a multi-class problem, you need to have different classes. So in our case, non-face is a class. So that means you also need a lot of negative examples. And this is normalization. So because the face has different size, so we want to do the normalization. We want to make to like scale it, or sometimes we need to turn angles to translate to the this size. So this is some data processing process. And in one of our workshops, we will introduce how can we do the data processing properly. So yeah, this is an application for the spam detection. It's a typical NLP application, and this is also a classification problem. You can have the the positive. You can have the positive examples. You can have the negative examples. In this case, the positive examples are spam emails, and negative examples are just the normal emails, right? You can turn your email into turn your message into some vectors, then send it to SVM to make the classification. So actually, I think before the deep learning, people avoid of using machine learning to solve this problem. Actually, people just use the rule-based method. So rule-based method actually works very well for this spam detection. So people just set different keywords, like well, if this keywords appeared, or if this grammar appears, if this thing appears, then that means this is kind of spam message, right? So people use the rule-based method to solve that. But one problem of the rule-based method is that, actually the enemy keeps innovating, right? So you can make so if you check 10 years the spam message 10 years before and check the spam email nowadays, totally different. So the enemy, I mean the spam message actually keeps innovating, right? So that means if we use a keyword, if we use a rule-based method, we have to update our rules maybe every week, or every year. So we need to update our rules. It's not a clever system. But if you have the machine learning, you can update your learning system, right? So the learning can be automatically. You can always learn, update your parameters by learning it, right? So that's why machine learning currently is dominant the spam detection in the field, right? So and again, the stock price prediction task. This task is to predict stock price at future date. Well, this is a of course this is a typical regression task because output is continuous and it should be some real value, right? So for example, this is the price at this date, and the next date I want to predict it must be a real value. It's not like a classification. I can't classify it into this one, or that one, right? It must be a real value. So it's a regression problem. But actually, I can also treat it as a kind of classification problem. Like I can predict it go up or go down, right? So it can be a binary classification, or actually we can make it as 3 classes classification problem. It can not up, not down, right? So well, yeah, it depends on your data, right? But normally we treat it as a kind of regression problem because we want to predict. For example, if you just predict the go up and go down, every time you can only predict one step because just go up you cannot predict go up how much, right? If you want to predict go up how much you go up, then it's actually a regression problem because you need to predict the real value, not to classify into a label, classify it into a class. So that's why normally stock price prediction is a kind of a regression task, right? So yeah, this is much more interesting. This is a typical regression task. So given the sequence, so I don't know what it is, it's protein structure. So give this sequence, we want to predict the 3D structures. I'm not sure whether you read the recent news. The Google, or they just release some model so that can predict all kinds of proteins in this world. So basically give us some structure of the protein information, then we can predict the structure automatically. This is actually very cool because you normally in chemistry we have to do a lot of experiments to try to figure out the structure, but with machine learning you don't need to do that. You can just predict the structure. So this is a very cool application. And again, in NLP, we have the machine translation, English to French, right? So Again, actually, in NLP, I mean, 30, 40 years ago, people just used the rule-based method to solve the machine learning problem because, to solve the NLP problem, like a regular expression, it's kind of a rule-based model, right? So still, machine translation can be solved by using the rule-based method because you know what's the correspondence between this word and that word, between this word and that word, and if you know the grammar of the English and French, you can actually write a lot of rules. When you have an English sentence, you can actually use your rule to match it into other languages. So rule-based system also works okay on the machine translation. But it also has a lot of problems. You need to write a lot of rules, and different people have different ways to express themselves. So that means even in the same language, people may have different usage of the words. So it's very hard to write a very good, perfect rule system to do the machine translation. And we have hundreds of different languages. We cannot write rules for all kinds of language. So that's why we need the machine translation. So Google Translate, I'm not sure a lot of you must use this one. So you input one sentence and you get a translation from them. So the Google Translation, again, actually, I think before the deep learning method, they use the rule-based. They hire some people who can write the regular expression, write the rule system very well. So there's a joke actually. Saying like 20 years ago, so the companies more likes to hire people who can write the regular expression than the people who knows machine learning. But now it's totally different. Machine learning definitely ruined this area. Now Google. Firstly, I think Google used some simple machine learning method to predict. I don't know what it is, kind of expert rule-based plus machine learning system. Later, I know they use LSTM, a variety of the recurrent neural network to do the translation. It works very well, but nowadays, you'll find actually the Google Translation is super good. It's much better than like 5 years before because nowadays they are using the transformer, which is new NLP models. It's very big. But the performance is very good, and they use a lot of pre-trained models. So that's a Google Translation. So in machine translation, so basically machine translation currently is a kind of solved problem. So I didn't see a lot of researchers still working on this area because people, it has been addressed very well basically by using the transformer models. So recommendation system, so people who bought the Hestai, which is a very famous book about statistical learning, then if you buy this book, then Amazon will actually give you a lot of recommendations, like you should buy this one and buy that one, like the pattern recognition and machine learning, the most famous PAMI book. So this is also based on currently it's based on machine learning. Previously, it's also rule-based method. So the company can hire a lot of people to write the rules. Say, well, we call it a knowledge base, right? Or knowledge graph. So it's like we have this product. Then I build a knowledge graph like this product 1, product 2, product 3, and we know there are some connections, and we can also define what's the weight between these two products, right? Like the connection of them is very strong, so I can give a weight like 0.8. Or the connection is very weak, I can just give 0.1. Or the connection, or maybe there are any connections, then we don't have any edge from this node to another node. So we can ask people to label this kind of knowledge graph. Then if you click one link or if you buy this product, it will automatically recommend some products. This is a rule-based system. But again, it's not feasible because there are billions of different products, right? You cannot write a root system cover all kinds of different products, right? And sometimes these products will be disappear. Sometimes we'll add new products. You have to maintain this graph, and you have to hire a lot of people to do this job, right? But nowadays, because we have machine learning, we can automatically mine this data, right? We don't build this data. We mine this data from the user behavior, right? So, for example, some people buy this book, that book, and that book together. We know, oh, there are some links. And if it happens to like hundreds of people, then we learn, the machine learning method can learn that, well, there's very strong connection between these links. And then it can automatically build this graph, right? So this is how machine learning can help the recommendation system. Okay, so there are we actually have mentioned this problem. There are 3 different kinds of classical machine learning problem. The first one is called regression. Again, this is kind of supervised method like the stock price prediction. So we want to estimate the parameters, right? We want to estimate the real values and continuous values. For example, the weight vs height, and the stock price and the horse price, right? So this is a kind of regression problem. It's kind of supervised problem, right? Because if we don't have the data, we cannot learn any parameters. So this is a kind of regression, supervised problem. And another is actually the most classical problem in the machine learning is the classification problem. And it's most of the time when we talk about machine learning, we want to use a supervised method. So if you have a startup company, every time if you have a customer, they want to make some application, the first question you want to ask to them is, do you have data? Do you have enough data to help me? So I have models, right? I have all kinds of models. I can, if my model cannot solve your problem, I can train a new model for you. But the problem is, do you have data? Right? So because the supervised learning method is based on data, right? So we want to estimate. So for the classification problem, as the digital recognition system, we want to classify the input image into 10 classes. And here, in this case, the simplest one, which is the binary classification. We have blue dots, we have red triangles. It's a binary classification problem. So basically, we want to estimate the class. So give me any data point. I want to classify it into some classes, right? I want to estimate the class label of that. So that's a typical classification problem. So when you do your project, or when you have a new application in the future, the first question you want to ask yourself is that a classification problem, that's a regression problem, or is that just another problem, as we here mentioned? It's, well, I don't have any labeled data, but I still want to, try to classify them, right? So that will be an unsupervised learning problem, like a clustering, right? So, for example, for the IMDb review. So a lot of IMDb review, we don't know. Well, now we have the score like well, 5 score is good, 1 score is not good, right? So if we don't have the score, we only have the language review, right? So we want to know whether it's positive or negative. We can still download them and to do some clustering method to classify them to cluster them into different clusters. So for example, here we have 3. We have those data sets. We have those data points, right? We don't know whether it belongs to. Well, here we labeled it as different labels, but actually we don't know how many classes we have here, how many clusters we have here, and for the clustering method, we can automatically cluster them into different numbers of clusters. In this case, we cluster them into 3 clusters. So in this case, we don't have any labels, right? We just want to learn the representation from the data itself and try to classify them into different clusters. And then we can also do the dimension reduction. So we have a lot of high-dimensional data. Some data is not like just a 2-dimension, right? Some data we have thousands of dimensions. For example, if you still remember for the first digits recognition example, we have 28 by 28, right? So if we put it into a vector, it's 748, right? So that means that vector, the dimension of that one is more than 700. So in a high dimension, you cannot image the high dimension space, right? You can still image, you can image the 3D space because we are in the 3D world. You can image the 2D space because we're in a 3D. You can plot it on you can project it into 2D space, but you cannot imagine the high dimensional space. You don't know what it looks like in the 4D. Sorry, in the 4D space, right? So yeah, even in the higher dimensional space, like I mentioned, 700, you cannot image that. So sometimes we need to do the dimension reduction. This is kind of unsupervised learning method we need to use. So that's the three types of typical types of the machine learning problem. So well, let's first check the supervised learning. So which is the most classical one. As I mentioned, for the supervised learning method, supervised learning problem, we normally have x and y. So x is the datum, so it's the feature itself. So in our digits recognition example, the x is the image, is a vector, right? And the y is label. In our task, in our example, y has 10 classes. It can be from 0 to 9, right? So that's the training data we have. So what we want to do is the learning system, the machine learning system, or the supervised learning system, is to find an f hat and make sure so that we want to learn an f so that give me the xi, and I input this xi into the f hat, and I can predict the yi successfully, right? That's the learning system. And for the prediction is, of course, give me a new point x, and I input it to the learned function f hat, and I can get the prediction y. Here, x is the new data, right? So this xi, yi is annotated, labeled data, and this x here is the new data, right? So basically, that's a supervised learning system. Well, we want to predict, not predict, we want to learn a function f to make sure give me the x, I can predict it y successfully, right? That's a supervised learning problem. And of course, in machine learning, we are studying what kinds of learning machines we can have, what kind of ways that we can learn this f. And the f can be very complex. Well, if you have a simple binary classification, linear binary classification problem, then f can be very easy, very simple. It can be just a linear classification problem, right? So it can be just a linear function. And if your problem is very complex, you need to have nonlinear function to classify the data into different parts, then f need to be a nonlinear function, right? And the deep learning, which I will introduce later of this semester, the deep learning is actually a stack of linear and nonlinear functions. Okay. So yeah. So here, this is a typical nonlinear classification problem because you cannot simply draw a straight line to classify them, right? You need to some curves to classify it into all these data points into two classes. So there's a typical nonlinear classification problem. So suppose we are giving a training set of n observations. That means observations observation means the training data points, right? So we have a set of n observations, and from x1 to xn. So x, as I mentioned, is a feature vector, right? It's a representation of the data. So and y is a label, right? In this case, because we only have two classes, right? We only have red triangle or blue dots. So we have two classes. So yi can be -1 or 1, right? So we only have two classes. So the classification problem now here is to estimate the fx from this data such that give me the xi, and if I input this fxi into the f into the function, I can predict yi, right? This will be the classical classification problem. And this f is actually this function. So this you see this green line is a kind of curve, but it's actually a kind of function, right? It's just a nonlinear function, right? So it's very complex, but it's just a function. Okay, so the machine learning, think about supervised machine learning, give me the data, give me the label of those data, and I want to learn a function. And this function can help me to classify the training data into the ground truth labels, right? So that's a classification problem. And here I want to introduce one simple list classification problem. As I mentioned, this is actually the simplest classification algorithm, and there's only one parameter, which is a k. Let's check that. So that's why we call it as a k nearest neighbors. So the algorithm is super easy. So for each test point x, so here test point, remember, test not training, okay? For each test point x to be classified, we want to find the k nearest samples in the training data. To classify the point x according to the majority vote of their class labels. Okay, here, that's our training data. We know we have two classes, red one, blue one, right? We have two classes. That's the training data in the feature space. And this black diamond, that's the new testing point. I put this point into this space. Let's assume we only have a 2D space, right? So two-dimensional. So I project my new point into this 2D space. For the k nearest neighbor, assume my k equal to 3, right? So that means for the algorithm, I want to find the most close 3 data points from the training data, because this data are training data, and I find there are 1 red, 2 red, and 1 blue. Then I do the voting. So while 2 is bigger than 1, so then I treat this new data point as a red one. Right? That's a classification. We predict the label. We gave a label, assign a label to this new data, to this new testing data. Right? This is, this is easy, right? This is the simplest nearest neighbor. This is simplest classification problem. So it's also applicable to the multi-class cases, right? So, well, we have two classes here. Well, think about we can add another, like a green, some green dots over here. And if k equal to 3, I can still find the most close to 3 points, and I do the voting. Which one is, which one give me the highest voting, right? Then I can decide which class it belongs to. So this is a k nearest neighbor classifier. And as we can see, k is very important, right here. So for example, let's think about k equal to 1. If k equal to 1, I only can choose the most close one, which is red. If k equal to 2, actually I will choose this 2. But if I choose this 2, I cannot decide because there are 1 red and 1 blue. So that means 50% to be the blue, 50% chance to be the red. If I choose 3, actually it will be red. If I choose k equal to 4, I think it will be red as well. But at some point, if I choose k equal to different numbers, I may have different predictions. So as you can see, the number of k is very important. So that's a parameter we want to learn from the data, which k should be we use. So now let's see this one. So if k equal to 1, actually, each data point can be one class. So basically, the partitions divide the space into different regions, and the boundaries are equal distance from the training points. So then if we know the labels, actually we can get the classification boundary. So if k equal to 1, we can actually get a clear classification boundary. Then then we can check if the data belong to this side, then it will be red. If this node belongs to this side, it will be blue. Right? That's the case when k equal to 1. And as you can see, this is a typical nonlinear function. Okay, so actually to do this, a basic assumption. Why can we say why the k-nearest neighbor works, right? A basic assumption is that the training set and testing set has similar distribution. Right? If the training set and testing sets are from totally two different data sets, they don't have the similar distribution, this method will not work. Right? So a basic assumption is that training set and testing set has a similar distribution. So that means assume that the training examples are drawn independently from the set of all possible examples. This makes it very unlikely that a strong regularity in the training data will be present in the testing data. So here in this case, for example, this is training data. This is the testing data. As you can see, the distribution are very similar. So basically, we have all the data together, and we try to sample some data from the total data to make it as the training data, and we leave other data as the testing data. So we train our model. In your case, find the k from here, then we test it over here. Right? And we, of course, to mirror it, we have to have some evaluation matrix or loss function here. To mirror the classification error, we do this one, right? So when yi not equal to fxi, so basically this is 1. So we calculate how many times, so we do the misclassification. So this is, we call this as a loss function, or it's kind of a risk, actually. So here, when we say we want to find out the best parameter, because in the k-nearest neighbor, there's just one parameter, which is the k, right? So in the learning, actually, we want to find out the best k I want to use. So how can I find it? So for example, k equal to 1 on the training data. Actually, the error is zero because when k equal to 1, we can find a clearly boundary that divide or that classify the data points into two classes. But we can find if I use this boundary on the testing data, the error is actually 0.15. Right? So this is for the testing data when k equal to 1. But if we make it a k equal to 3, is actually, as you can see, the classification boundary becomes smoother. But on the training set, because k equal to 3, because k equal to 3, we cannot clearly classify the points into two classes. So we have some error on the training set. So on the training set, we got some error, which is 0.07. But on the testing set, actually the error become lower. So previously, when k equal to 1 on the training set, it's very well. The error, but the error on the testing set is 0.15. But here, the error is 0.13, right? So which is slightly lower than the previous case. So this problem is called as the generalization problem. So basically, the real aim of the supervised learning is to do well on the testing data that is not known during the learning process. Right? So in the learning process, we don't know the testing data. The basic assumption is that the testing data has a similar distribution with the training data, but we don't know that, right? So that's the aim of the supervised learning. So we want to choose the value for the parameters that minimize the loss function on the training data. But this is not necessarily the best policy, right? For example, here, if k equal to 1, so error equal to 0 on the training data, this is perfect for the training data, but that doesn't mean perfect on the testing data, because although the distribution is similar, but it's not exactly same, right? So that means we want to learn the machine to model the true regularities in the data and ignore the noise in the data, right? So that means we need to do some sacrifice to get the best k. To get the k, maybe not works perfectly on the training set, but it can work well on the testing set. So that's called the generalization ability. So that's why in your project, some students ask me about your project ideas, and I suggest you find different data sources, right? For example, if your application is just based on one data source, maybe you can get a very good accuracy on this data set, but you may find it doesn't work on some other data set, right? So that means we want some, diversity of the data set to give us a good generalization ability of the machine learning method. So again, this is a case of the k equal to 1, case of the k equal to 3, the arrow becomes smaller, become lower, and actually k equal to 7, again, the arrow of this one increase from 0.07 to 0.13, and this arrow from 0.13 decrease to 0.11, and when k equal to 21, actually this arrow actually decrease from 0.13 to 0.11, and this arrow also decrease, right? So from 0.11 to the 0.009, right? So basically, for the k nearest neighbor method, as k increases, the classification boundary becomes smoother, and the training arrow can increase. Well, it's not always. Sometimes it decreases as well. It depends on your data, right? It's not a problem of the method. It totally depends on the distribution of your data and depends on how you sample your data. So, so the learning process is actually we want to choose the best k. Right, we want to choose the best k to give us good results on the testing set, but not on the training set. How can we do that? So we need to define a new split, which is called the validation split. Be careful here, because in your project, if you want to get good marks, say this is a valuable project, then you need to define your data set. You say, in my data set, I have a training data. Well, let's assume it's a supervised learning problem. If it's an unsupervised learning problem, then let's forget it. So if it's a supervised learning problem, typically in a data set, we have a training data, we have a validation data, and we also have the testing data. For the testing data, the assumption is that we don't know that. It's just over here. During the learning process, we don't want to touch the testing data, but we have the validation data. For the validation data, we can get by using the validation data, we can get the best value of the hyperparameters in this case, which is the k. Right. So that means we hold all the validation data and the narrow arrows on this one. Right. So I can check this. If I choose k, okay, that's the training accuracy, or that's the training arrow. But that's a validation. Another value is a validation arrow. And try another k. Test on the validation set. So find the best k on your validation set and use that k for your testing set. Okay, you cannot. So actually, this happens a lot to some new PhD students. So when we publish papers. It happened actually several years ago when I was a PhD student. It's not me; it's my classmates. So what he did is like he directly try to find the best parameters from the testing data. So every time he train a model, he tests on the testing data. Every time he train a new model, get a new k, for example, test it on his testing data, and until he finds the best results, then he publishes these results. It's not a lot, okay? So it's a wide rule because you use your testing data to find the best model. It's not a good practice in research because it cannot guarantee your model is the best one. You only can touch the validation data. You must choose your best value, best hyperparameters from the validation data, and directly use that value on your testing data. Okay, so that's the case. You cannot you cannot learn on your testing data, right? You have to test on your testing data, but learn on the training data and find the best value on the validation data. So that's why we need 3 different splits of the training, validation, and testing, right? So in your data processing steps, you need to be careful of this one. Okay, so let's finish this. So yeah, so this is a handwritten digits recognition system. So let's assume we are using the k nearest neighbor here, 7 nearest neighbors. So this is the input value, and if I use the 7 nearest neighbor, I got this 7 outputs, and when I do a voting, I know that because this side is from the training data, right? I know this 0, 0, 0, and this is 6. So when I do the voting, so 0, I have 6 zeros, so I know this is 0. And for this one, for example, 2, I have 3, 2, I have 3, 8, and 1, 7. So my output might be 2 or might be 8. And 4, definitely 4. And this 9, actually I have only one 9, but I have, for example, in this case, if I use k equal to 1, if I just 1 nearest neighbor, actually my prediction will be right. But if here I use 7 nearest neighbor, the answer is wrong, right? So that's why we want to select the best k in the validation set. So this is the miniest data set. And okay, so in the k nearest neighbor, when we say the closed one, when in the 2D dimensional space, for example, or even in the higher dimensional space, when we say the closed one, or we want to find the k nearest one, the nearest or closed, so we need to use some distance measurement to calculate the distance between 2 points, right? We need to calculate distance. That means we need to define the distance function. So here, in this example, the distance function can be the raw pixel distance between 2 images. So we just calculate the difference between, because you know in the picture, in the image, for each pixel we have a value from 0 to 5 to 5, right? So we can calculate the distance between 2 pixels. So we can calculate one by one and summarize them together. So there's a raw pixel distance between the images. So with this distance function, and if we have 6-day k training examples and 10k testing example, actually in the 6-day training example, you can divide some parts as a validation example to help you to find the best k. And actually, as you can see, KNN can give us 5% classification error. That means even with the simplest k nearest neighbor method, the accuracy can achieve 95%, which is very high, right? But now if we have many better methods like deep learning CNN method, the accuracy is just very close to 100%. It's 99.9 or something. So let's summarize this one. So basically, KNN is a simple but effective classification procedure. It also applies to multi-classification classification problem. So here I just put it as a binary classification, but actually this is a multi-class classification problem, right? Because we have 10 classes. It's a multi-class classification problem. The decision surfaces are nonlinear. This is a boundary. This is a decision surface, right? It's a nonlinear. It's not a linear function, and the quality of the prediction automatically improves with more training data, right? With more training data, you can get the it will be more close. You can predict the distribution more close to the testing data. And only a single parameter, right? So different from the current deep learning method, you have millions, even billions of parameters. Here, you only have one single parameter, which is k, and easily tuned by the cross validation. And the disadvantage is that what does the nearest mean, right? That means you need to specify a distance metric. In our digits recognition example, well, it's very easy. We define the distance as a pixel difference between 2 images. But for higher dimensional data, the distance metric is very important. Different distance metric may lead to different results, right? And of course, we have big computational cost. You have to store and search through the entire training set at the test time. Right? So that's how it works. Give me a new data points. I have to calculate the distance between these new data points to all the points, to each point in my training data. Right? It's a large computation. So think about if we have millions of training examples like from the ImageNet. It's impossible to use a KNN algorithm to solve that, because every time you want to do a classification, you have to calculate 1 million times of distance and ranking them, right? It's nearly impossible, right? So that's why later we introduce some other algorithm like SVM or some linear classification problem. After the training, actually, we can discard, we can throw away those training data. We just leave the parameters. But in KNN, we have to keep those data and the parameter. Although we only have one parameter, but we have to keep millions of data during the testing, right? Of course, this problem can be solved by some other tricks, which I will not introduce today. So, okay, so that's our first session. So let's have a break, and later I will introduce regression and some other algorithm. So let's come back maybe, this is 2 and 10. Let's come back to 15. Okay, let's have 5 minutes break, okay? Okay, so let's come back. So let's come back to this one. So, okay, so well, we just introduced the classification, right, which is a very typical problem in the machine learning. Now let's discuss the regression problem, which is another very important problem in the machine learning. So if you want to do the stock price prediction, house price prediction, or price any, predict any real values from the different data, from the different factors, then you will need a regression. So in the regression, suppose we are giving a training set of n observations. Again, observation means the training data. So here, which are the blue dots, and x1 to xn, n data points, and yn, right? So here in the classification, y is actually a label, right? So if it's a binary classification problem, y is -1 or 1 or 0 or 1, or for example from 0 to 10 if it's a digits classification problem. So, but in the regression, y is a real value. Right? It can be continuous. It can be like, for example, if a stock price is like a horse price, it can be 1 million, 3 million. It's a real value, right? So give me this x and y. Give me n observations. For the regression problem, I want to predict a function that can fit this data, and then give me a new input. For example, xn plus 1, and I want to predict yn plus 1. I want to provide the I want to predict the new value based on the new input, but it has a similar trend of the previous input, right? So the regression problem is to estimate yx from this data. So KNN regression. So again, KNN can be used for the regression problem, which is the simplest one regression algorithm. So for each test point x, we want to find the k in the KNN classification is easy, right? For the new test point, we just find the k nearest neighbors and do the voting. Then for the KNN regression, for each test point x, we just need to find the k nearest samples xi in the training data, and we need to know their values yi. Then the output is just the mean of their values. Right? It's easy. For the classification problem, we just need the label, so we do the voting. So for the regression problem, we need the value, so we do average, right? So the output value of the yi is actually the average of all the k nearest neighbors of the new input xi. So again, we need to choose, actually learn the k, right? So you want to choose k. So here n equal to 100. That means we have the 100 training examples. Again, we need to choose the value of the k to give me the best accuracy of the prediction, right? So let's check this example, which is a polynomial curve fitting. So this green curve is actually the true function, right? Which is not a polynomial actually, it's just a wave curve, right? So the data points are uniform in x. So from 0 to 1, I have 10 points. Start from 0, 0.0, 0.1, 0.2, 3, 4, 5, and until 1. right? And the y value is actually different, right? So y value is not uniform, and actually we have some noise, right? So some value actually not on this perfect function. So we will use a loss function that mirrors the squared arrow in the prediction of yx from x, and the loss for the red polynomial is the sum of the squared vertical arrows. So basically, again, let's assume I already get some function y, right? So then input is x, and that's the value I predicted by using my function, and I use this function to minus the target value, which is the ground truth value. And if this value is quite big, then that means this function y is not good, right? So I want to use this as a kind of loss function to optimize my learning process to get the best function, right? So well, that's a y, right? So because we assume this is actually a polynomial classification, polynomial regression function, right? So I assume the y x w, this function is a polynomial. This is a polynomial function. You know what is polynomial function, right? So basically w0 plus w1x plus w2x squared, and until wm x raised to the power of m, right? This is a typical polynomial function. So I assume this polynomial function can feed this data. So that means in the learning process, I want to learn the parameter of w0, w1, w2 until to the wm. I want to learn these parameters from those data. And once I got the testing data, I just need to input my x, input the w I learned from training data. I can predict the value, right? So that's a function I assume. Then to train this one, I need some loss function, and this is a loss function I just defined with this loss function. If this value is big, that means because xi is fixed, right? So if I have testing data, the xi is fixed. The w can be changed. So if this value is big, that means current w is not good enough. So I need to adjust my w a little to make sure this value as small as possible. So if you learned optimization theory before, so what we want to do is to use the training data to minimize this loss function, right? The process of minimize this function is to get the best w, to get the best parameters, right? That's the learning process. So some feeds to the data, which is the best. So let's assume one m. So in the polynomial function, we have we have a hyperparameter which is m. So it decides the complexity of this polynomial function. For example, if x equal to 0, that means y x w is just w0, right? Just a single straight line. So of course, then this red line is not good enough to fit this data, right? So think about it. If this is the function you learned, then give me a x. For example, give me a, well, if x equal to 1, I can predict the value. It's okay. But if x equal to, for example, this is 0.6, then if that's a function, the value will be, the error will be extremely big, right? So that means if m equal to 1, this is not a good one. So here, if m equal to 3, so m equal to 1, so the y x w will be equal to w0 plus w1x. So this is actually a straight line in the two-dimensional space. It's just straight line. Then the straight line, of course, this line can move, depends on the parameter w we learned. But then no matter what the angle it is, this is not a good fitting of the data, right? So this is still not good enough. But if m equal to 3, actually, if we can have a good learning of the w, and actually that will be the polynomial function. And actually, as you can see, it's very close to the true function. But at some point, if m equal to 9, right? So although it can fit each data point very well, right? It fits this standard point, but it has a big difference between the real function we want to predict and the predicted function, right? There's a big difference. So although it can fit the training data very well, but if we have a new data point, for example, if we have 0.2, sorry, some value between the 0 and the 0.1, for example, this one. This is a true function. That's a value. That's a ground truth value. But if I use a predicted f, the value will be here. So that means it's not a good prediction. So we call this as actually the overfitting, right? So it's called overfitting. It's fit the training data too well, so it's overfitting, but it has little generalization ability. So here we plot the arrows. So as we can see for the training, when we have different m, the accuracy actually slightly, the arrows becomes lower, but and when m equal to 9, the arrow becomes to 0, and this is the testing set. For the testing set, well, the trend is similar to the training set, but when m equal to 9, the training arrow is super big because we overfit the training data. Okay. So training arrow goes to 0, but test arrow increases with the m. Okay. So that means we need to have a trade-off between the model complexity and the accuracy, right? So if the model has many degrees of freedom as a data, it can fit the training data perfectly. Right? For example, in our last case, in the polynomial case, if m equal to 9, we can have a very complex polynomial function, right? So it's like w0 plus w1 x until, well, w9 x raised power of 9. So super complex polynomial function, right? And we have 9 parameters to learn. So when m equal to 9, so of course we can fit the training data very well, but we cannot produce good results on the testing data because it's overfitting, right? As we can see, the objective, the machine learning, is the generalization ability, right? Finally, we want to use the model on the testing data, but not on the training data. So we need to be careful of the generalization ability. So yeah, we can expect the model to generalize well if it plans the training data surprisingly well, given the complexity of the model, right? So if the model complexity, so basically we want to find the right complexity of the model. Well, sometimes, of course, the model is, if it's more complex, that means it can fit the training data very well, but it cannot generalize well to the testing data. So here is an example. So from m equal to 0 to m equal to 9 of the polynomial function, and if we learn the parameters from w0 to w9 of that polynomial function, we can actually find when m equal to 9, some of the coefficients, the w is super large, right? So that's a sign of overfitting. That means this function is fit to the training data very well, but it's impossible to have a good generalization ability because some parameters are so big. So to prevent overfitting, there are 2 ways. The first way is to add more data than the model complexity. So for example, if n equal to, this is for the nice order polynomial, right? So in our previous example, we only have 10 data points, and we set the m equal to 9, and if you still remember, the polynomial function is very different from the true function. But here we simply just add 5 more training examples, and m is still equal to 9. Then the learned function actually becomes to this, slightly close to the training function, the ground truth function. And actually, if we increase the training examples n equal to 100, even m equal to 9, it's a complex function, right? But as you can see, the model, the length function matched with the ground truth function very well. So one way to prevent overfitting is to give more numbers of training data. That's why actually we always say for the machine learning, or actually nowadays the modern machine learning is based on the data set. Right? So why people prove the deep learning works so well? In the deep learning models like CNN, as I mentioned, we always have millions of parameters or even billions of parameters. In here we only have nine polynomial, nice order polynomial function, just 9 values, just 9 parameters. Think about if we have 1 million or 1 billion parameters, and if we only have 100 examples, it's impossible to train a good model. It will be definitely overfit of your training data, right? So that's why in the deep learning method, we normally require lots of training data. For the ImageNet, there are millions of images, and to train a transformer, to train a bird, right? People use 10 gigabytes of text from online, right? So so people use so many data to train the deep learning models, because in deep learning models we have so many numbers of parameters, right? So that's one way to prevent overfitting. Add more data, right? Add more field, add more data, then you can have a better prediction, no matter how complex of your function it is. And of course, complex function can fit your data well, because as you can see here, so if m is small, like 0 or 1, no matter how many data you have, you cannot fit the training data, right? Because m equal to 1 is just a straight line, right? M equal to 0 is just a flat line. No matter how many data you have, there's no direction to modify it, right? So you have to find the best complexity of the model based on your data, right? So that's one way to prevent overfitting. So in your project, for example, if you say, well, my data set is not big enough, I only have like 100 training examples, for example, in your case, you say, well, I cannot download a big data set. I don't have a good machine to process those numbers of data set. And sometimes for some students, I collect the data by myself, so I only have 100 training examples. In that case, it's nearly impossible for you to learn some complex models. So make sure you don't use deep learning models. You can just use the KNN, because it's less complex models. Yep.
And what about when we use pre-trained deep learning models?
That's another case, yeah. That's a good one. So in the pre-training deep learning models, that's because the pre-trained models has been pre-trained very well on large numbers of data, right? So, and proved the thing for deep learning, that's also a good thing of deep learning models, is that the generalization ability of a deep learning model is super good. So that means if you pre-train your deep learning models on dataset A and directly test your deep learning model on like dataset C, when I see dataset A and C, they are both image dataset, right? Then the performance actually is okay, right? Because the generalization ability of the deep learning model is good. And the generalization ability of that is good because it trains on large numbers of data, right? So that's a different story. And I will introduce one in the later of this semester when we have a lecture actually called Deep Learning Basics. In that course, I will introduce like you have pre-training and you can fine-tuning. And sometimes if your data set is super small, you cannot even do the fine-tuning. And once you do the fine-tuning, actually it will be overfit. Right. So that's another issue. But for this one, if you don't have a big data set, and if you want to train from scratch, right? So when we say training, we normally say train from scratch. We don't consider the pre-trained models. If you want to train from scratch, make sure you use a less complex models, right? If you have, well, for example, some of you I have a good machine, I have a GPU, I want to work on the image processing, and I have millions of images, like open images from websites, and I want to train a big model. well, okay, you can use a complex model, and in that case, actually, you can still use the pre-training models, and you can save your time of training. So, but that's another story. Okay, so yeah, add more data points is always good to the your machine learning models, right? So data is very valuable and sometimes can be very expensive actually. So another way to prevent overfitting is called regularization. So we penalize large coefficient values. For example, over here, as we can see, when m equal to 9, and if I only have 10 points, and that's the parameters I learned from those 10 points, and some parameters are super big, that's not a good sign. So we can penalize this situation. We can say, well, we don't want this value. If this value is too big, well, this is not a good direction to optimize. So that means I can add a penalty value over here, which is actually the absolute value of the W. W is a parameter, right? Absolute value of the W square. So that means if your W is super big, like this one, 1 million. So if it's super big, then the square of that one will be very big. And because it's a loss function, that means by plussing this one, your loss function will be super high, right? So if your loss is super high, that means this is not a good way to do the optimization, right? So I don't want to introduce optimization to be much more complex, but you only need to know is that if this error function, if this loss function is too big, that means the model cannot be converged. You have to choose some lower parameters. So as you can see, and there's another hyperparameter which is lambda. This lambda basically decides how much power you want to choose to penalize this this coefficient values. So in practice, we use a validation data set to choose this lambda, and as you can see, here is the case. Even we only have 10 points, and when m equal to 9, and if we set lambda equal to -18, when we say, well, we want to penalty allowed, and actually we get this function, right? So you can set different, well, this is ln lambda, sorry, not a lambda, it's a ln lambda, right? So that's why it's negative value. Okay, so that's another way to deal with the overfitting problem. I introduced this one because, well, last year many students mentioned, well, I tried a model like even a simple SVM. SVM also has a problem of the overfitting. I will introduce SVM later. It also has some hyperparameters you need to tune that on your validation data. Some students mentioned I have the problem. Some students mentioned, well, I got really good results, like 99% accuracy or 100 accuracy on my training data, but I use my model on the testing data, the accuracy is super low, just 2%, 3%. What's the problem, right? So that's the reason, right? That's if you made this problem, go back to this slide. That's a problem overfitting. Check your model, right? Check whether you set right regularization lambda, right? So if you're using, for example, the polynomial function, if you're using SVM, even in SVM, we also have this penalization, we call the regularization term. Check whether you set the right parameter, right? If you don't know that, you don't know what happened of your algorithm, right? Okay, so yes, you can see if ln lambda equal to minus infinite, which is like this, like the previous value we learned, some parameter are super big, and actually if ln lambda equal to -18, and it's become very normal. Some parameters are not so large, so that means the generalization ability of this one will be good, will be like this. Okay, so that's one way to deal with overfitting. So yeah, how to set parameters. Actually, I introduced this one just several minutes ago. So we have to divide your data set into 3 subsets. Training data is used for learning the parameters of the model. Validation data is not used for learning, but used for deciding what type of model and what amount of regularization works best. So for example, for the k-nearest neighbor, you can use the validation data to choose n, right? So for the polynomial data, you can use the validation data to choose the lambda and m, right? So lambda and m are 2 parameters in the 2 hyperparameters in that model. And the testing data is used to get the final unbiased estimate of how well the learning machine works. And we expect this estimate to be worse than on the validation data, right? Because on the validation data, you test it several times, you find the best value, but on the testing data, you only can test it once, right? So use the hyperparameter learned from the training data and validation data and test on the test data, right? So if you have your own data set, if you download existing data set, for example, if you download ImageNet, or if you download the COCO, which is another image data set, or if you download some NLP data set, they already have the official split. They already give you, this is the training split, this is the validation split, and this is the testing split. And for some data set, actually, like if I'm working on the visual question answering, which is an area like you have an image and you have natural language question, and our model want to answer that question. In our area, we don't publish the testing data. We keep the testing data as a secret. We put it on our own server. And if some people can only train their model on the training data and test it or validate it on their validation set, then if they think their model is good enough, they submit their results, their model to our test server, and we only gave him the accuracy, like, wow, you got like a 78% accuracy on our testing data, but we never tell you what the test data looks like. So that's a way to, avoid people like cheating. Say, I can train the data, I can train my model on the testing data, I can get the best hyperparameter on my testing data, right? It's not good for research, because normally when we want to publish a paper, we normally compare the models, right? This one has 90% accuracy, this one 95. We want the value, those numbers can be trusted. Right, so that's why in many areas nowadays we keep the testing data on our own server and ask people to submit their results to the testing server. We never release the testing data. And in your case, if you have your own data, you can definitely split it into training, validation, and testing. Okay. So generalization problem in classification, which is very important. This is definitely underfitting. Underfitting means that, think about the polynomial function. If m equal to 0, it's just a flat line, right? Just straight line. It's impossible to use that simple function to classify those so complex data, right? So it's called underfitting. And sometimes we have an overfitting problem. So the function is so complex, it can fit the training data very well, but go to the testing data because distribution might be slightly different. So the accuracy will be actually low, right? So avoid overfitting. So if you meet the underfitting problem, try to improve the complexity of your model, right? To make it works like this. So if you have the overfitting problem, as I mentioned, that might be because your model is too complex. So you can decrease the parameters. You can, increase the number of data points, or you can add some regularization, right? So avoid overfitting. So finally, we want you to got some models like this to fit the data, but has some generalization ability. Right? That's the key of the classification problem. Okay. So, this is about the optimization. I don't want to introduce optimization to be, but in the deep learning part, I will introduce optimization about the deep learning models. For this part, I will not introduce this one, but I think we still have some time. I can talk about the SVM. So, Yeah, so support vector machine actually was the most classic classification problem you have ever seen. So we know the KNN is simple, it's easy to use, but one problem of the KNN is that you have to always carry your training data during the testing. Right? If you have millions of training data, it's impossible to make it applicable on your phone, right, or any application, right? You in your phone, you want to recognize your face. Well, think about it. You have to compare how many faces you have. So that's why we need some other more clever classification classification algorithm. So SVM, supported vector machine, is actually one of the most classical one. Actually, before the deep learning method, nowadays I guess no people use the SVM because deep learning is so hot. Deep learning, the deep learning models or CNN models, neural network models, it's another classifier which I will introduce next few weeks. So, but before that, SVM is one of the most classical one. And actually, in your project, because maybe you don't have enough data, maybe you don't have a good GPU to train your own deep learning model. Well, of course, you can use pre-trained models. But if your data is small, still you can use SVM as a kind of a really good algorithm to classify your data. So let's try this binary classification. Well, let's assume we were doing a binary classification problem. So I only want to introduce a binary SVM. So for the SVM, again, we can use that to serve the binary classification problem, or we can use it to serve the multi-class classification problem. It's called multi-class SVM. So here I only want to introduce a binary SVM. Okay, so giving training data xi, yi for I equal to 1 to n, right? Xi is a feature vector, and yi, because it's a binary classification, which means yi is just -1 or 1. So we want to learn a classifier fx such that fxi bigger than 0 if yi is positive 1, and fxi is smaller than 0 if yi is -1, right? So that means give me a f function and give me a new point xi. If I input that one into the function, if it's bigger and equal to 0, it's a positive class. If it's smaller than 0, it's a negative class. This is a classical binary classification problem. And if you move this to the left side, so that means we want to do this yi times fxi bigger than 0 for correct classification, right? So that's a binary classification. So we have two examples for this left example and right example. So now we need to talk about the linear classification and the nonlinear classification, right? So for this one, can we draw a straight line to classify them into two classes? Yeah, so we can draw a simple straight line to classify them into two classes. So that means we can simply learn a linear classifier to classify them. And for this one, it's impossible, right? So there's no chance that you draw a single straight line to classify them into two classes, right? So that means sometimes we need the linear classification, sometimes we need nonlinear classification. So yeah, so this is linearly acceptable and this is not linearly acceptable, right? So yeah, this is the case. So here is one red inside the blue. So it's nearly impossible it's totally impossible to draw a straight line to separate them, right? So it's not linear acceptable. So that means we need some nonlinear function. So let's introduce a linear. So actually, the deep learning method is for the nonlinear classification. So basically, if you have a lot of examples, so this is actually the ideal case. So normally in the real world, the case is like this and this, right? So the linear classification is always the ideal case, actually. So a linear classifier has this form. So because it's a straight line, right, we can simply draw a straight line to classify them. So that means we can assume fx equal to wx plus b. Right? This is so x is the slope, b is the bias. Right? So this is simply the form of the linear classifier. So this is x. So for example, if we
if this is x, this is y, and we know fx bigger than 0 is class 1, fx smaller than 0 is class 2, and we know this y-axis actually can divide that into two parts, so the fx equal to 0 is actually a simple classifier, right? So basically in 2D, the discriminant is a line, so W is normal to the line and B the bias, and W is known as a weight vector. So basically, if I have, so in the linear classification problem, so basically it's like, well, I have some data. The first assumption I make is this is a linear classification problem. I only want to learn a linear function to divide them into two parts, right? So that's my first assumption. So based on this assumption, I assume that I can say, because it's a linear one, so I can say my my classifier is Wx plus B, because this is if you learn the mathematics in, I think it's a high school mathematics, right? So Wxb is a function of a straight line, right? So that's a function I want to learn. So based on those data, I want to find out the best W and find the best value of the B. If I can find the best value of W and the best value of the B, I can successfully divide the space into two parts, right? So that's a linear classifier. So the whole optimization process to learn W and B. So, well, this is a 2D space, again in the 3D space. So in the 3D space, it's slightly different. It's not a straight line anymore. So, but still, it's a linear classification, but we can use Wx plus B. It's not a straight line, it's a plane, right? So think about it in the 3D space. I don't have paper here, yeah. So think about, I have 2 parts of data. This is one part of data, this is one part of data, and I want to learn a plan to divide it into 2 parts, right? So this is in the 3D space, right? It's not a line anymore, but it becomes a plan. So that means we can still use Wx plus B, but this W is not a single value. In the 2D space, W is a single value. In the 3D space, W has 3 values, right? And of course, we can go to the higher dimensional space, 4-dimensional, or in our first the image case, the 28 by 28 is 760. I can remember the number. It's more than 700 dimensions, right? So that means we are learning. It's not a plane we can image, right? It's a it's a high-dimensional plane, hyperplane. So yes, as I mentioned, for KNN classifier, it was necessary to carry the training data during the testing. But for linear classifiers, you can see after we learned this W and B, after we got this line, right? If we have let's go to 3D space. If we already learned the W, that means I already learned this plan. After I get this plan, after I have a new point, if this point belongs to this side, it's a light. If this camera, sorry. If the points belong to this side, it's a screen. Right? So I don't need to keep my original training data. I just keep this plan. So that means, for linear classifier, training data is used to learn the W and then discard it. Right? I can throw them away. I don't need any training data anymore. So that's why we need a better classifier, right? So only W is needed for classifying new data. Actually, we also need B, right? So normally we ignore B, but we need this one. Okay, so that's a linear classifier, and so linear classifier sometimes also called as this. The perceptron classifier, so given a linear separable data X labeled into 2 categories, -1 and 1, we want to find a weight vector W to make it work. So basically, we want to separate the category into 1 to n, right? So how can we find a separate hyperplanes, right? How can we? So this is related to optimization. This is related to how can we find the best W, right? So the whole machine learning is about give me the X, give me the Y, and give me a lot of this data, but I want to fit this function into those data so that I can find this W and B, right? So how can we do that? So one way is called the perceptron algorithm. So
we can reformulate this function to this one, and so fxi equal to wxi plus w0. So because w0 is actually it's just a simple parameter, so we can write it as this one, and so equal to wxi, where the xi equal to xi and 1, w equal to w and w0. So the initialization, we can say, as an initialization, we can set the parameter as 0. Well, basically, we can set it as any value. It's just initialization is not that important. We can, in deep learning or some other algorithm, we just do the random initialization. We just assign a random value to that one. Then we cycle through the data points x and y. If xi is mismatched, then we need to adjust this w a little. We need to adjust the w to, like, the new w will be equal to the old w plus some alpha times the sine of fxi. So sine means positive or negative, right? So if fxi is bigger than 0, this is 1. So if fxi is smaller than 0, this will be negative 1. So that means if fxi is correct, so alpha will be equal to this will be plus, right? So if fxi is negative 1, because we have sine which is equal to negative 1, so this will be minus. So until all the data is correctly classified. You may be confused about this, so let's just check this. The figure will be easy. So we have two parts. The blue one and the red one, and this is the initial plan. So we set w equal to 0. That's the initial one. And as we can see, the second step is cycle through a data point xi, yi. So I just choose the first the one value xi, and I check this xi. The fxi is actually at the left side of this one. So that means it's a mismatch. It's a misclassification. So that means this value will be equal to negative. So I need to adjust my w slightly from this side to this side. The steps I want to adjust equal to the alpha times the xi. Alpha is some parameter, some hyperparameter you can set. So that means I can drag this plan from here to this place. Then, as you can see, if I drag this one from here to here, I can classify it into the right place, right? So that's the first step. But I also have some other points to check because I have to do all the data points. So so that means I can adjust this plan, this side, this side, this side. So until I find out the best position to put it in the middle of the classes. Right? For example, at some point, after I do all the points, maybe at some steps, I will find a plan over here, right? So I find the line over here. So if I find this, I can actually successfully divide the space into two parts: one part for the blue and one part for the red, right? So that's that's the simplest way to explain the optimization process. Okay. So basically, the learning process is to use your training data to adjust this W until you can find the best plan to divide your data into two parts, right? Because you have the binary classification. Okay, so we're running out of time today. So this is basically linear classification. Based on linear classification, we have the supporter vector machine. Basically, we want to find the largest margin, but we will introduce next time. So that's it. Thank you very much.